Hi everyone. In today's video, we are going to use the PyTorch framework to solve a classification problem. In the video 1 of this lecture series, we were able to solve a regression problem, which was more like a curve fitting problem, where we had an independent variable x, and using this independent variable, we had to estimate y, which is a dependent variable, and the entire problem revolved around finding a functional form f, which could approximate y as closely as possible. One thing which we were able to observe in the video 1 is the fact that y is having a continuous scale. It could take values in a real number range. But in our scenario, in this video too, we are going to consider the domain of y, or the possible values which y can take, as finite, which is only 0 and 1. We call such sort of problems as binary classification problem, and the functional form f becomes a decision boundary which is able to segregate the zeros and ones from the data based on the set of features x which are available. Ideally, this is what we are going to do. We are going to consider two features, x1 and x2, just to make the visualization easy and to make the understanding even simpler. And we will have a set of target values y, which can take only two values, 0 and 1. X1 and X2 can take any values, we don't really know. This is what we are going to simulate first, and on the top of it we are going to use the knowledge from our last class to build a model which will approximate zeros and ones from the data. But over here, the first and foremost step we need to do is to create the data using sklearn's functionality. We will jump straight into the code and try to see what we can do to create the data in the first place. So this is how the code ideally looks like. We do some initial level imports, which are the basic imports done for the EDA libraries like NumPy, Pandas, and Matplotlib. We use another plotting library, which is Plotly as well, which will make graphs a bit more interactive. We use Torch, and we are going to use make blobs from sklearn to create our own data sets. So let's dive into the documentation of make blobs to understand what all parameters we are having. So it ideally takes a number of samples. We are going to take some 1,000 samples of the data, and number of features, definitely we are going to take two features to make understanding easy. Centers is basically 2 because it's a binary classification problem, and cluster standard deviation, if you make it a bit high, then both the clusters will be quite mixed with each other and it will be practically difficult to separate them. We will definitely induce some noise amongst both the clusters so as to make sure that there is some level of error which is there while classifying, and we don't get 100% classification at any stage. Now let's look forward and see how we are going to create the data for our problem. We use the make blobs, and then we say that n underscore samples is equal to 1,000, and then we select the centers as equal to 2, and then n underscore features is equal to 2 again, and we select random underscore state as 13, and standard deviation, which is cluster underscore std, as something like 3. And it is let's see what it is actually going to return. So we jump into the documentation, then we say that it is able to return x and y and centers will be returned only when if you put return underscore centers as true. So as of now it's just going to generate x and y, and let's see what we get. Yeah, so this is how the x and y is generated, and we will put it in the form of a pandas data frame to make the visualization a bit easy. So yeah, this is how the data frame looks like. It is having two features, feature 1, feature 2, and target. That's what we generated above. And the x1 and x2 are analogous to feature 1 and feature 2 over here, and the target is having values ones and zeros as we expected. Further, if we look into the distribution of the target, it is pretty much balanced. Now we are going to see how the data looks visually and try to see if we are able to visually segregate zeros and ones from the data in the first place before trusting our model with the segregation task. This is how the plot looks like, and over here if we just hover around the observations, we can clearly see that the yellow and blue observations are clearly separable. There are some observations which are kind of which are going to be misclassified. For example, this blue observation is over here amongst all the yellow observation, while this yellow observation is over here amongst all the blue observations. So definitely we are not going to get a 100% accurate classifier in this scenario, but we will be able to approximate the separation boundary between the two classes to a great extent. We are going to convert the numpy arrays x and y in the form of torch tensors, which will be used in the model development. And this step is pretty much simple as we have seen from the previous video. So we are just going to use torch dot from underscore numpy. This will convert the numpy array x into the vector torch tensor x, and likewise capital Y will be torch dot from underscore numpy y, and if I just reshape it in the form of a column vector or a column tensor x and y, we are able to get it. We also convert y into double just to keep the notation consistent. We print the shape and also the data type associated with it. Yeah. So this is what we are getting, and this is what we also expected, that the torch tensor of x will be of size 1000 cross 2, which will mean that it has two features, x1 and x2, and y is of shape 1000 cross 1, and both the tensors are torch.float64 data type. We have to make sure that in the training phase, whenever we are considering the weights for training, the weights should carry the same data type as the torch tensors which are fed as an input. Now we will proceed further with creating our custom model class, and before that we will delve a bit into the mathematics and see what exactly we are trying to achieve. So we will try to understand how the shallow network structure is going to look in this scenario. So this is our first node, which will be the x1, which is the first feature we are having. This is the second node, which is x2, the second feature we are having. We consider a bias node as well, and all of them are combined at one node over here. So this takes the weightage of form 1, this takes the weightage of form w1, a weightage of form w2 over here. So over here we get something like z is equal to w1 x1 plus w2 x2 plus b. So now this is a linear activation function as we know, but to make a decision boundary in such scenarios, we always consider something called as a sigmoidal activation function. So over here we are going to use an activation function which is going to look like this. Az is equal to 1 upon 1 plus e raised to minus z. Now this is going to give a decision boundary which will be 1 and 0, and 1 will happen if if az is greater than 0.5 and 0 else, greater than or equal to 0.5 and 0 else. So this will act as a decision boundary over here, and then it is going to do a prediction of whether it is a 0 or 1. So this is just a one layer shallow network which is involved in making the correct prediction. So we can see how a forward pass is going to look like. So this is exactly how a forward pass is going to be. There are some input parameters like x1, x2, bias is definitely going to be there. There are some weights associated, and we will use a linear activation function to get the value of z at this point of time. And then for the eventual decision making, we will use a sigmoidal activation function based on the probabilities. We will say that the output is going to be 1 or 0. Now, like we discussed in video 1, we considered something like mean squared error as a loss metric for enabling the backward propagation step. We can't use the loss metric in case of a classification problem, but what we will use is a cross entropy loss, or more precisely a binary cross entropy loss in classification problem. So what it will do, it will take the probability values which the sigmoid activation function is giving, and then try to see how closely the probability values are to the true value of y. Just to give a hint, this is how the cross entropy loss function is going to look like. So it is going to be minus of y log to the base 2az minus 1 minus y. You can also use a natural log as well, but I am using the log to the base 2 because this is what is there in most of the theoretical literature. That's it. Now, just to give an overview of how this loss function is going to look like, the value az, if it is close to 1, let's say if the value of az is 0.9 and the actual prediction y is also close to 1, then this will imply that the loss is tending to 0. Now, if AZ is 0.9 while the actual value is close to 0, this will imply that the loss is pretty much high. It's not actually tending to 0, maybe it is pretty much high. There is actually a limit to the loss function when we consider a binary cross entropy, but as of now, yeah, we just consider the loss is not going to be 0, which is ideally the scenario which we need. Uh, Over here there is something called as a misclassification which is happening. It is like properly classified over here. So again, the reverse holds for the cases where we have the value of az close to 0 as well. Let's say the value of az is 0.1 and y is tending to 0, then the loss will be tending to 0 again. It's properly classified. And if az or the probability is zero point 0.1 while the y is tending to 1, then it will imply that the loss is not tending to 0. It's misclassification done in this in these cases. So we will try to make sure that the losses are as minimal as possible. Just see the scenario when this case happens. So if I just plug into the function y is 1, this term will be vanished. Only this term, the first term, will remain. So we will have 1 over here by default, and log of 0.9 will be a term which is close to 0, as we have a negative sign as well, because log 1 is very much equal to 0. So anything close to log 1 will be 0 as well. So this is like an intuitive way of thinking how you can use the cross entropy loss function when you are having the probability values. Now just consider a scenario where y is equal to 0. This first term which I am highlighting, this term is going to vanish. What I am going to be left with is this term, and over here we are going to have values which are not tending to 0 but definitely very much away from 0. So a misclassification will be there because we want the losses to be minimized as much as possible. So just by looking into the properties of how a logarithm curve is behaving, we can just try to estimate the fact that the values close to 1 in case of a binary classification will give you less loss when the actual value is 1, while the values close to 0 of a sigmoid function will give you less loss when the actual value is close to 0 or actual value is 0. So this is how the function actually behaves. Now if we try to open the function a bit, this is how the loss function is going to look like. we will have minus y log 1 upon 1 plus e raised to minus w1 x1 minus w2 x2 minus b. This is for the first term, and then we will have a negative sign, and then 1 minus y log 1 minus 1 upon 1 plus e raised to minus w1 x1 minus w2 x2 minus b. You can look at this expression and try to figure out how complex the computational graph is going to be. While it is very much possible for us to do that on pen and paper when the number of observations are much less, but in scenarios where even only two observations are present, drawing computational graph on pen and paper and trying to estimate the forward and backward path as easily as we had done in the previous video is not going to be a good option for us. We will allow the AutoGrad functionality of PyTorch to take care of it and create those graphs in the backend. So let's jump into the code and build the custom model as we have discussed in the last video as well. So just like in the last video, we are going to use the nn.module over here, and then we are going to set an initializer which is going to just take no arguments at all. We will use the super functionality to initialize the parent class, which we did over here. Now we are going to initialize the trainable parameters of the model. Now if we look back and try to see what are the trainable parameters we are trying to achieve, the parameters w1, w2 and b are the trainable parameters. Like we had in our regression problem in the previous class, w and b were the trainable parameters. We have three trainable parameters in this problem statement. So the trainable parameters are going to be declared in exactly the same way as we did previously. We will be using nn dot parameter, and we are going to use torch that rand n. This is just one type, one parameter which we are considering, and the d type, it's better to use the data type corresponding to the data only, so as to avoid the type mismatch errors while we are training. And requires underscore grad is equal to true will mean that this is a parameter on which a backpropagation should be applied. So we do the same for W2 as well, and we do the same for B. So we initialize the parameters W1, W2 and B over here. Like we discussed in the video 1, we will have a forward step as well, which is just going to take one parameter X, and it will return a sigmoid activation function. So we just spoke about a sigmoid activation function over here. So it should be declared in the first place as well. So this is what we are going to declare. So that is going to be nn dot sigmoid. So whatever you are going to use in the forward class needs to be declared in the initialization so that the training becomes easy. So this is the documentation for torch.nn.sigmoid, which we have used over here, and it says that it is going to take input in the form of an x. So whatever we defined as z over here, this is going to be put as an input, and this is exactly what we did in the parameter step. So we considered the z value, which is w1 into x0, which is the first feature, w2 into x1, which is the second feature, plus b, which is the bias. Now we are going to call the model, which is going to look like this: custom model, and there are no parameters. We do this, and then we set up the criterion or the loss function as torch.nn.max. BCE loss. So this is the binary cross entropy loss, and the entire loss function which I explained over here, this loss function, this is what we are using in our code. And we also select the optimizer over here, which is going to be torch.optim.std, and over here we just use model dot parameters, because these are the model parameters on which a backward prop is going to be applied, and the learning rate I select as 0.01. That's it. So yeah, now we proceed further to the most easiest as well as the most important step, which is training the model for epochs in range. Let me train it for some 1000 epochs, and this is all judgmental. So we first try to find out the output corresponding to the model when we pass the input data X. The second step is to find out the loss. And for finding out the loss, we are going to use output dot view minus 1 comma 1. So these are a little bit of experimentation which I have done at my end to make sure that the code runs bug free. If I don't do this view minus 1 comma 1, you are definitely going to get an error, and on analyzing the error and reading about it, you are going to make this change. The entire reason behind this is the fact that the binary cross entropy loss expects a column vector to be matched with the target vector y, which is having zeros and ones as values. Now what we do, we do the optimizer dot zero underscore grad. We ini optimizer. Sorry. So we initialize all the gradients in the optimizer to 0. We initialize the backward propagation step as well, and then we update the weights associated with the model using the optimizer. So the same steps which we used to do. So this is the forward propagation step, and line number 2, this is the forward propagation step. We calculate the loss over here. We equate all the gradients to 0, and then we initialize the backward propagation step, where we calculate different gradients corresponding to different parameters of the model, like W1, W2, and B. And then we do the gradient upgradation, or we update the weights with the gradients with a suitable learning rate, which was selected as 0.01. Now if we want to periodically visualize the loss which we are getting, this should be fine. We print epochs plus 1, loss is equal to loss dot item. That's it. We run the code and let's see what we are getting. So this is what we are getting. The loss started at 2.56, and over the period of time the loss reduced drastically, and this is actually a quite a decent cross entropy loss which we are getting. After some point the value stabilized as well. So this is how we were able to reduce the loss. And if we try to find out how the outputs are looking like, let's try to see the first term values of the outputs. These are all the probability values which we are getting. But our main concern is to segregate the zeros and ones and try to find out how the zeros and ones are associated with the model which we are having. Like the exact same thing which I mentioned over here, that if the value of the sigmoid function is above 0.5, mark it as 1, else mark it as 0. So how exactly we are going to accomplish that task, that's what we are going to do over here. And on doing so, how many of the ones are correctly classified and how many of the zeros are correctly classified, that's also a thing which we need to check. So we will do all these things, but for that we have to convert the torch tensors into numpy. So what we do, so we do as an output, and we say that we use this detach dot numpy, and actual is equal to y dot detach dot numpy. So we were able to convert the torch tensors to numpy arrays. Now we are going to enforce a decision boundary over here, which is going to look like this. So we say that wherever the parets are greater than or equal to 0.5, it should be 1, else it should be 0. That's it. Okay, so this works. I think there shouldn't be any error. Yeah. So now we are going to analyze one important metric which is called as an accuracy. From sklearn.metrics import, let me import all the metrics possible, and from there I am going to import something called as an accuracy score. An accuracy score takes into account the actual values first and the predicted values later, and the accuracy of our model is about 99%. So this was a very balanced data, and it was having only, you can say, two classes as well as two features, so the accuracy is pretty high. And we will try to find other performance metrics as well from the data, which is like recall. And if you read a bit about it, this will tell you how much of the actually one values are correctly predicted. So it's about trying to find out that if a value is one, it is correctly predicted or not. Likewise, we can do the precision as well. So from what we are able to see is that the accuracy, recall, and precision score are pretty much close to each other. So the model did a good job in learning the patterns, and it was able to segregate the zeros and ones from the data. Now, since we have got some decent enough performance, we are going to understand how to interpret the model parameters in the first place. So we have the parameter W1, which is coming out like this. This is the parameter W2, and this is the parameter B as well. So we got these three parameters after performing an entire chain of forward and backward propagation for about 1,000 steps, and these are the final list of parameters. So the W1 is coming out to be minus 0.02. Let me simplify it and let me write it down over here so as to make the understanding a bit easy. So we get W1 as minus 0.02. We also have W2, which is equal to 0.927, where we write it as 0.93, and the value of B is equal to minus 1.8. Minus 1.8. Now, what we are saying is we have got a decision boundary, which is AZ, which is equal to either 1 or 0, and the possibility of 1 is there only when 1 upon 1 plus e raised to minus of w1 x1 minus w2 x2 minus b is greater than or equal to 0.5. Yeah. So let's take any random point from the data and try to validate this assertion. Even though these are approximations, we will just try to validate whether our understanding of a decision boundary and whatever we have done matches with the result we are getting in the from the code or not. So for that, we draw a random sample from the data frame, which was our input data frame. This is the random sample which we are having. So it is having the value feature 1 and feature 2, and the target is 0. Now let's try to compute the sigmoid function using the parameters which we have in the first place. So it's going to be like 1 divided by bracket 1 plus np dot exp, and minus w1 is here. The value of w1 is minus 0.02. If we put the minus sign to it, it becomes 0.02 into, and the first feature value is 4.029019. You can do it in much sophisticated way, just that for validating the results I am just hard coding it and to make the understanding a bit clear. And then it's minus of W2, which is minus 0.93, minus 0.93 into uh, in brackets minus 7.307885. Yeah, and then we have to add the bias term. The bias term is minus of b, which is 1.8 only. So we do that and we get the value as something. This is a probabilistic value which is very much close to 0. Now the hypothesis that it should be 1 only when it is above 0.5 is very much validated over here. Like this value of the probability value is very close to 0, and hence the actual target should be 0, which is clearly seen. Now I draw another sample. Let's hope that I get a positive sample. No, I'm getting a negative again. Make an attempt, again a negative. Yeah, we get a positive sample over here. We copy the code and change the feature 1 and feature 2 values. The feature 1 value is 4.71309. 71309. This I don't need. And over here it is 11.047706. That's it. It comes out to be a value much closer to 1. The probability value is much close to 1 and the target is also 1. The hypothesis that if anything is above 50% should be mapped to 1. The decision boundary which is coming out of this sigmoidal function is exactly what we need and it is fitting the data properly. So we can say that the model is able to do the predictions and the decision boundary is very much coherent to a good extent, but we see that the model is going to suffer from a small drawback. So the way we have initialized the model over here, we were able to do that because we had only two features in the data, x1 and x2. Let's suppose in the real world data sets we have multiple features in the data, like we may end up with 100 200 features or even more than that, or maybe 40 50 features. Even the significant amount of features in the data we have to do this initialization that many amount of times, so we need to avoid that. So this could be done quite intelligently using a linear activation function which does the entire process implicitly from its own end, and we don't have to worry about making the multiple initialization over and over again. So that's what we are going to discuss now in the modified implementation of our function, which is going to look like this. So we start with the same process of creating a class for tabular classification, and we use the same nn.module over here as well. We have an initializer which is taking two arguments, which is input dimension and output dimension. And the first thing we do is to instantiate the parent class, which is done like this: self dot, and then we declare the first forward connected layer, which is of form nn dot linear. It takes into account the input dimension, it takes into account the output dimension as well, and also the data type. So just remember, just 10 minutes ago I was talking about having the data types consistent for both the tensors and as well as the activation functions which we are going to use. Like the parameters w1 w2 should have the same data type as the data type which the tensors are having, which in our case was torch.float64. So I'm going to use the same convention over here as well. What it does is it takes into account, this linear activation function takes into account the input and output dimension and initializes all the weights inside the activation function, which is w1 w2 and b over here, of the same data type as the input data it is about to receive. If we don't do that, then there is definitely going to be a data type mismatch. So one has to be a bit careful when selecting the data types within the activation function, so as to not get that error. Likewise, I can use self dot sigmoid. Let me make it as this only, sig is this, which is nn dot sigmoid, and then we can use the forward layer, which is self comma x, and we get the output as self dot fcx, and the final output as self dot sigmoid output, and we return the output. That's it. So we practically reduced the code to a significant level, and this is just one shallow network using one fully connected layer, which takes into account a linear activation function. So whatever is happening over here is exactly what we have mentioned in our documentation as this. So the first step, z is equal to w1 x1 plus w2 x2 plus b, this is exactly what is attained over here in this layer, and we are getting out as the z which is there in our explanation, and this az is the second out which we are getting, which is coming out of a sigmoid activation function. So this is what we did. We are going to declare the input dimension because we have to do it explicitly, and output underscore dimension, let it be 1. Yeah. So now we just follow the usual steps we have done. I'm just going to copy the code as it is and just change one small thing. I'm not running anything. I'm just copying the code as it is. This is what we had. And this is what we had for the training step. The code will remain as it is. The only thing which is going to change is the initialization. So the initialization is going to be like this. We take the tabular classification, and it has the input underscore dimension as 2, or let me make it as 2 comma 1. If I scroll up a bit, yeah, that's it. So this is how we were able to make our class for forward propagation as agnostic to the number of input parameters in the data. We are going to run the code and hope that it runs without any error. Yeah, it ran without any error, and we are able to get results over here as well. Just look at the loss we are getting over here, 0.37796, and look at the loss which we were getting over here, 0.33608. So not this, I think, yeah, 0.303077. So there is a small deviation in the loss which we are getting in both the cases. So this is 0.03077. I scroll down and we are getting 0.03779. So the procedure to calculate is exactly the same. What we have done in this module is exactly what is happening over here in the model which is self-defined. This model, it's exactly the same thing. The only deviation which we are getting is because of the way the weights are being initialized. Over here we are using a random normal initialization, but over here it uses a uniform initialization. Let's look a bit about it in the documentation to make things a bit clear. So yeah, this is the documentation for torch.nn.linear. We considered the input features and output features as it was mentioned, and we considered the bias as well. Whether if we set it to false, then the bias won't be considered, but by default it is true. And we also considered the data type as well. Now if I scroll down a bit, it is clearly showing that the values are initialized to minus of root k to root k uniform, where k is the number of input features. So in our case, the weights were initialized as uniform 1 upon root 2 minus comma 1 upon root 2. So any uniform value between this range was picked up as the initialization for all the weights, and the same was applicable for bias as well. So because of the different initialization done, like over here we use a random normal initialization, while over here we are using a different initialization, a uniform initialization, we are getting different eventual values, but the performance is not going to deviate much. So the initialization plays a very important role in such cases as well, but that's a topic for a separate discussion. So the main agenda of the video was to cover how to build a custom classifier model from the learning which we had from video 1, which was based on regression. We applied a lot of concepts from regression over here in classification as well. And as we move further, we were able to generalize our model in a much better way. So this is how a shallow network is going to look like in a classification problem, but the class for performing the classification in deep neural network is not going to be much different from the one which you are seeing on the screen right now. Just that we will have few hidden layers as well in order to make the network deep, and the forward functionality will have a lot more lines of code, because one layer will be connected to other, and there will be different outputs which are being propagated, along with the fact that some dropouts and other regularizations will be there. So that's it for the video. In the next video, we are going to understand how to create the data loaders and apply a train split on the data to fit the model. Thanks for your time.